In the previous lesson, we have presented the different elements related to the calculation of a water profile in a prismatic channel between an upstream underflow gate and a downstream reservoir. We will now analyze the different possible flows that can occur in such a system. As a reminder, here are all the possible upstream and downstream conditions. At the upstream side, we can have a free surface flow controlled by the gate, a submerged hydraulic jump, or a free surface flow detached from the gate, thus without control of the gate. At the downstream end, for subcritical flows, we can have a simple direct connection or a spill, and for supercritical flows, we can have a spill or a hydraulic jump pushed back in the reservoir. So, how to start to determine the flow profile? Well, we first need to know the discharge. We will start by assuming a free surface flow controlled by the gate, which allows us to calculate the discharge using Torricelli's formula. With the discharge Q, we can calculate the normal depth HU and the critical depth HC. This will allow us to determine if we expect a mild slope or a steep slope profile. Let us consider the case of a short, mild slope channel. If the gate opening HV is below HC, the initial assumption of a free surface flow controlled by the gate is valid, because we are in the region of supercritical water profiles that depend on upstream boundary conditions. So in this zone, here, we have a M3 profile starting with a depth HV. As the channel is short in the present example, the M3 profile does not reach the critical depth before the end of the channel. For a downstream water level below HC, we have a simple spill, and the water profile is as illustrated. If the downstream level increases above the downstream end of the profile M3, but below the sequent depth M3' here, the downstream level leads to the formation of a hydraulic jump that is pushed back in the reservoir, so without influence on the flow in the channel. If the downstream level further increases above the sequent depth M3' here, a downstream control flow profile starts from the downstream level, and this leads to the formation of a hydraulic jump. Then, for further increasing downstream water levels, we have a submerged hydraulic jump. Note that the submerged hydraulic jump is illustrated here for a M1 profile, as the downstream water level is above HU, but it could happen also for a M2 profile. In the case of a submerged hydraulic jump, the first estimate of the discharge is wrong. It has to be corrected, as the discharge is influenced by HM, the depth of the roller area. So we start a trial and error procedure. We assume a first value of HM. With this value, we can recalculate the discharge and then the new normal and critical depths. We can then calculate H2 in two different ways. First, from the downstream flow profile, starting from the downstream water level. In the case illustrated here, it will be a M1 profile at the downstream level is above HU. This is the water depth H2A here. We can also calculate H2 using the submerged jump equation recalled here, and we obtain a second estimate of the H2 depth, that is H2B here. If the two estimates of the H2 depths are different, it means that the discharge is wrong. So we have to try with another value of HM. But how to know if we should increase or decrease HM? As demonstrated in previous lessons, if we increase HM, the discharge decreases, and H2B calculated from the submerged jump relation increases. Then, According to the water profile slope theorem, the new downstream flow profile will have a milder surface slope because the new discharge is smaller than the initial value. Here, the downstream point connecting with the downstream water level here remains unchanged. As the new discharge is smaller than the first estimate, the normal depth HU will decrease, and the new water profile, that is still a M1 profile, will be less steep, and thus below the initial one. As a consequence, the water depth H2A decreases. And as we can see, if H2B increases and H2A decreases, the two depths become closer to each other. We further increase HM, and finally we obtain the equality between H2A and H2B. The two calculated with the two different techniques, H2A with the downstream flow profile and H2B with the submerged jump relation. When the two depths coincide, it means that we have found the correct flow profile. So for a short mild slope channel, the possible flow profiles according to the downstream conditions are summarized here. Note that the hydraulic jump and the submerged jump could occur for M2 or M1 profiles, depending on the gate opening, the discharge, and the downstream level. In the case of a long, mild slope channel, the situation is analyzed as done before. The main difference is that the M3 profile cannot reach the downstream end of the channel. Therefore, a downstream spill or a jump pushed back in the reservoir are not possible anymore. A hydraulic jump will occur for any downstream level. If this downstream level is below HC, we have the first situation. A M2 profile here develops from HC at the downstream end of the channel with a hydraulic jump here, and this M2 profile then spills in the reservoir. If the downstream level increases, the hydraulic jump moves in the upstream direction and eventually may become a submerged jump. If the gate opening A here becomes very large, the flow might detach from the gate. At the location of the gate, the water depth is now H1, larger than HC. This water depth is used to calculate the discharge. However, as this depth H1 also depends on the discharge through the downstream controlled flow profile here, we have again a trial and error procedure. Let us now analyze the case of steep slope channels. In this case, the procedure is similar. We first consider a free surface flow below the gate and calculate the discharge. Then, with this discharge, we calculate the values of the normal and critical depths and check that HV is below the critical depth HC. The flow profile that can develop below the gate is a S3 profile if HV is below HU, or a S2 profile if HV is above HU. Anyway, these profiles tend to the normal depth and can thus be infinitely long. In the present example, we have a S3 profile. If the downstream water level is below HC, the flow just spills into the downstream reservoir. For an increasing downstream water level, we first have a hydraulic jump that is pushed back in the downstream reservoir, if this level is below the sequent depth of the S3 profile at the end of the channel. Then, for higher values of the downstream level, we have a hydraulic jump or even a submerged hydraulic jump, for which the same trial and error procedure as in the mild slope case should be used to connect the hydraulic jump to the downstream controlled flow profile. However, in this case, we don't have the water profile slope theorem to guide the process, as it is only valid for mild slope channels. This implies that the convergence of the process is more difficult, but it is still possible, for example by using small HM increments to approach the solution. Finally, different possible situations for a steep slope channel with a small gate opening below HC are summarized here, considering different possible downstream conditions. If the gate opening now becomes larger than HC, we have again a detachment of the flow from the gate, and we can have a control section at the gate with the critical depth that can be obtained, for example, from the water depth H0 in the reservoir, if we assume that the velocity in the reservoir can be neglected. In this case, with HC here, a S2 profile will start from the critical depth, and depending on the downstream conditions, we have a simple spill, a hydraulic jump pushed back in the reservoir, or a hydraulic jump in the channel, here. In the fourth case, the downstream profile is completely subcritical, and the subcritical depth H1 at the gate should be estimated by trial and error, as described before, because the discharge will depend on this depth as indicated here. So we have seen that there is a great variety of possible solutions for the flow between an upstream underflow gate and a downstream reservoir. In any case, the calculation starts with the discharge and then the normal and uniform depth to know the type of profile. Then, the final solution will depend on the downstream boundary conditions, with a possible trial and error procedure in the case of a submerged hydraulic jump or a flow detachment at the gate. Goodbye.